Welcome to Year 10 Physics. What this video is about how to do motion questions. Year 10 Physics has motion and energy. I'll do another one for energy questions. So the idea of this one is that you need to download the question sheet for motion, and the link will be in the description. Once you've printed it out, come back and be ready to do some work. What you'll need to know is your formulas. And the way that this video is going to be structured is that I'll introduce the question as per your sheet, then I'll walk you through it. The idea is that you need to attempt the questions to a certain extent on your own. If you find some of the questions too easy, you can easily skip those ones and go straight to the end where the difficult ones are. The formulas are here. This can be a bit confusing. So in these physics equations, S represents distance. A is acceleration, V is velocity, and U is initial velocity. So we've got distance equals velocity multiplied by time. This is the same equation, it's just been rearranged. We've got velocity equals initial velocity plus acceleration multiplied by time. This is the same equation again, but we've isolated the acceleration. So if you've got a question where they're asking what the acceleration is, you can use final velocity minus initial velocity divided by time. This is Newton's second law, where force equals mass times acceleration. And this one's a little bit trickier. We've got distance equals initial velocity multiplied by time plus half acceleration times time squared. It looks really complicated, but really this equation is just a combination of a couple of the other equations. Works really effectively. It's basically, you can, if you don't have a final velocity, this is an equation that you can work out the distance that's traveled so long as you've got initial velocity, time, and acceleration. This is a little triangle to help you use the F equals ma equation. Force equals mass times acceleration, and what you do with this one is you cover up the one you want. So if you want to find force, you cover it up and you've got mass times acceleration. If you want to find acceleration, you've got force divided by mass. And if you want to find mass, you've got force divided by acceleration. See how it's over the top. A lot of you will be comfortable just using that equation without needing the triangle. Sometimes with some questions, you're going to need to do a conversion between kilometers an hour and meters a second. And this is the simple way to do this. So to go from kilometers per hour to meters per second, you divide by 3.6, whatever the number is, and then you multiply going the other way. That's where we're going to start. So you want to do these conversions. Remember, that's how you do them. So pause the video now, do those questions, and then come back. How did you go? I'm sure some of you just kept going. But this is what you should have got. We can see that with the kilometers per hour, the number's always bigger than the meters per second. In order to go from a big number to a little number, you have to divide. In order to go from a little number to a big number, you have to multiply. Technically that's not correct, but it might help you remember how to do it. A kilometre is bigger than a metre, so you've got to multiply to go from metres to kilometres. Alrighty, I want you to do these ones. Force equals mass times acceleration is the law. I want you to do that now. Okay, 12 times 9.8 gives us 117. 0.023 times 355 gives us 8. So these are the answers that you should have had. Hopefully you did. This one down here is a little bit trickier. You need to really know how to use your calculator to do this one. So if you can't do that, what you need to do is get somebody to teach you how to use your calculator properly so you can do that. Here's the first kind of real question where you've got to use a formula. They're scaffolded. So the first thing I want you to do is circle the variables you're given in the question. We're given a velocity and we're given a time. So you'd want to highlight velocity and highlight time. Wants you to find the distance, so it wants you to find s. Is there an equation that has all of those in it? You bet there is. It's s equals v times t. So this is the equation we're using. This is how we know what we're using. Some of you will be able to do this without highlighting or circling and all that sort of stuff, but nothing wrong with it if you need to do this, at least at the beginning. Hopefully we get better at it. Distance equals velocity times time, 40 times 90, because it's in meters a second and it's in seconds, so 3,600 meters. You could put it at 3.6 kilometers if you wanted to. Next question. How fast will a car that is moving at 60 kilometers an hour be going if it accelerates at a rate of 5 kilometers an hour every second for 10 seconds? Convert the velocity to meters per second. You can do this either way. You can do the conversions at the start, or you can do the conversions at the very end once you've worked it out. So what we have here is we have an initial velocity, we have an acceleration, we have a time, and it wants you to tell it the final velocity. So we've got a u, an a, and a t, and we have to find v. Is there a formula that has those four variables in it? Of course. V equals u plus at is the equation that you need to use for this one. And then we just sub the values in. V equals 60 plus 5 times 10. 110, see I've kept it at kilometers per hour. And then what I need to do is I need to divide it by 3.6 to get it in meters per second, because that's what the question's asking us to do. You have to have the units with each of these answers. 30.6 is just a number. It's meaningless. 30.6 what? Milliliters? 30.6 light years? Like, just doesn't mean anything. You have to have the correct units. Next one. So we need to find V, and we have T, and we have S. Is there an equation? Yep. V equals S over T. It's just that rearrangement of the first one, which is S equals velocity times time. So we've got 100 meters, 12.5 seconds, 8 meters a second. This is probably one you could have done without knowing this equation. Like, this is the sort of thing that you've done a lot of in your time. Plane traveling at 240 meters a second reached 650 meters a second if it accelerated for 15 meters per second. So we need to find the time. So time is how long? Time is what we need. We've got an initial velocity, we have a final velocity, and we have an acceleration. Is there an equation? It's the same one as the other one, but it's just in a different arrangement. V equals u plus at, and t is what we need to find. So it's a little bit trickier to work our way through this one. 650 equals 240 plus 15t. You subtract 240 from both sides and you end up with 410 equals 15t divided by 15. 27.3 seconds is how long it would take accelerating at 15 meters a second squared to get from 240 to 650. What distance does a car travel if it moves at 90 meters a second for 7 seconds? Easy. S equals V times T. 90 times 7, 630 meters. That car will travel that distance. Question 8. How fast will a car that's moving at 10 kilometers an hour be going if it accelerates at a rate of 15 kilometers an hour every second for 6 seconds? So the variables we have initial velocity, acceleration, and time. We're trying to find velocity. We're using the same equation again. Substitute the values in, we get 100 kilometers an hour. Isn't that neat? Well done, me. You need to make sure that you're trying these questions, not just looking at the answers. The average speed of a runner that runs 1.6 kilometers a mile in 4 minutes. So if you've heard of the 4-minute mile, that was some astronomical thing that in the early 20th century they were saying nobody can break this. And then once somebody broke it, a guy called Roger Bannister was the first one, but once somebody broke it, heaps of people broke it. It was a mental thing. I think now they're running under 3 minutes 40. I'm not 100% sure on that. Anyway, circle the variables you're given. A distance and a time. And we've got to work out the velocity, average velocity. So average velocity equals distance divided by time, 6.7 meters per second. The fastest Usain Bolt goes is somewhere around like 13 meters a second, so twice as fast as that. However, he's not running for 4 minutes. He's only doing that for 10 seconds. A peregrine falcon diving at 40 meters a second. That's pretty fast, but it's actually a reasonable estimate. To reach a speed of 90 meters per second, holy crap, if it accelerated at 12 meters a second. What we're after is time. We've been given initial, final velocity, and an acceleration. V equals u plus at again. Bunch of questions using this equation in one form or another, but there's really only 3 equations in Year 10 motion. 90, final velocity equals 40, initial velocity plus 12 times t, and we end up getting 4.2 seconds. Some serious acceleration. Oops, there's a mistake there. That should be per second squared. Anyway, so Cam rushing out of a classroom question out loud who had a mass of 52 kilos. Cameron applied a force of 350 newtons. What would L's acceleration be? We need to find an acceleration. Force equals mass times acceleration. So if she weighed more, her acceleration would be less. That makes sense. If someone's heavier, they're not going to bounce off as quickly, are they? So F equals ma is our equation. 350, that's newtons. 52 kilos times A is the acceleration. It's going to bounce off at 6.7 meters per second squared. That's pretty bouncy. That's not going to be very nice. Car reached a velocity of 70 meters a second after accelerating at a rate of 2 meters a second squared for 8 seconds. What was its initial velocity? So we've been given a velocity, a time, and acceleration. We need to find initial velocity. So V equals u plus at again. Even I'm getting bored with how often this one's in there. 70 x initial, 54 meters a second was the initial velocity. And this is one you could have just worked out without using the equation. You could have done it intuitively. However, it's good to do the setting out in case you get it wrong, then you can get some marks. Question 13, a car changed velocity from 48 meters a second to 96 meters a second in 5 seconds. What was its acceleration? Let's have a look. Our variables, the ones that we have, need to find acceleration. Velocity, time, initial velocity is what we have. Again, V equals u plus at. 9.6 meters a second squared. That's a pretty impressive acceleration. Newton's second law can be used to calculate its person's weight force. Compare the weight of a person on Earth with the weight of a much heavier astronaut on the moon. So this person's almost 3 times as heavy, but gravity is much smaller on the moon. So for acceleration, we just use the g value because that's acceleration due to gravity. So on Earth we use a g value, substitute that in for a of 9.8 meters a second squared. Relative to that on the moon, it's much smaller, about 1/6 of what we have on Earth. So using the F equals ma equation, you're going to come up with these two. Force on Earth 715 newtons, force on the moon 393 newtons. So far less, even though the astronaut is ridiculously heavy compared to the person. So more than 3 times as heavy. But still much less force pulling down, so their feet wouldn't hurt as much. Interesting tidbit on the moon when they went there. One thing they didn't expect as much, the astronauts, was the fact that their momentum stays the same. So even though the pull of gravity towards the ground was less, so they could get higher, I suppose, when they were bouncing. When they tried to stop, they still had all the momentum of something that weighed 246 kilograms. So they're falling over quite a bit. Because it was, probably seemed very strange feeling light, but then having all this momentum that made it difficult to stop. Perth to Sydney, 5.5 hour flight. What's your average velocity? And then do the conversion afterwards. So these are the ones we have, SV and T, V equals S on T, so distance divided by time. So 596.4 kilometers per hour, but it says convert it to meters a second. So I've got to use this conversion. And it should come out with 165.7 meters per second. Question 16. Skydiver falling at 20 meters per second accelerates when their main parachute fails. Their emergency parachute opens 6 seconds later. How far did they fall during this time, ignoring wind resistance? Quite often in physics questions, if it doesn't make mention of a particular force, they want you to ignore it. I'm explicitly stating it here to ignore it. What do we have? We're looking for a distance. We've got a time. We've got an acceleration, which is just g, because it's a skydiver. And we've got an initial velocity. Which equation are we using? Actually, you should have done this or attempted this question already. We're using this one. Distance equals initial velocity times time. We got both of those. Halves just a scalar. A, we've got that, and we've got t squared. Ends up that in that 6 seconds, they fell almost 300 meters. That might be a little bit scary. Train travelling at 55 kilometers an hour. Driver passes out and falls to the floor. He pulled a control level, or he or she pulled a control level. The train began accelerating 1.5 meters a second squared. That happened for 2 minutes. And how far did the train travel in those 2 minutes? So we've got a distance, we've got an initial velocity, we've got an acceleration, we've got a time. But we're going to do a conversion into meters per second. So 55 divided by 3.6. The reason we do the conversion first is because we've got this in meters per second. We can't use that in kilometers an hour and that in meters per second. We need to change the 55 into meters per second. When in doubt, use meters per second. Don't go with kilometers per hour. Initial velocity times time plus half acceleration times squared. Ends up going 12.6 kilometers in those 2 minutes. The thing is, this acceleration is crazy if it's going for 2 minutes. I would doubt that this train, well, this train probably couldn't get to it, but I wonder how fast the maglev trains go. I think Japan has some super fast, almost no friction on them. Question 18, a rocket's taken off from a launch pad in Houston, Texas. Draw a free body diagram of the forces involved. Here is your free body diagram. It's launched, so the thrust force must be bigger than the gravitational force. Comfortable with that? So the arrow is longer. Has a mass of 2.2 times 10 to the 6 kilos. That's actually realistic. And this is realistic as well, 20 meters per second squared acceleration. What's the amount of thrust provided by the fuel? How much force is there for that mass to accelerate with that amount of acceleration? The first thing we need to know is what's really going on here. What does the thrust need to do in order to get to that acceleration? The thrust is accelerating the rocket upwards, but also countering the force of gravity. So this is the acceleration upwards, and this is the force of gravity. The amount of thrust needs to override that force associated with this acceleration, plus the force of gravity as well. It's not as simple as pushing upwards with the thrust and everything's great. The gravity of the Earth is still pulling it down. It's got to override that. So the net force, to get it to 20 meters a second, something of that mass, so we just multiply them together. So 4.4 times 10 to the 7 newtons. The force of gravity on this rocket is 2.16 times 10 to the 7 newtons. That's about half. And that makes sense because 20 meters per second and gravity is going at 9.8. Force of the thrust, you add them together. So in order to get this acceleration and override gravity, you need to have a thrust this big. I wonder how you went on that question. If you're clever, you might have got that. Question 19. Oh, here we go. Trolley loaded with watermelons. This is usually a maths question, isn't it? Only in mathematics does somebody buy 100 watermelons. Constant velocity in a car park. Shopper loses control and the trolley accelerates down a slope, crashing to a stop as it strikes a car. Free body diagrams to show the forces involved. 1. When the trolley is being pushed. 2. When it's rolling down the hill. And 3. The moment it strikes the car. So what do we know when the trolley is being pushed? Loaded with watermelons is being pushed at a constant velocity. This is our key here. So when there's a constant velocity, what do we know about the forces? They are balanced. So gravitational force, upwards force, stopping it from going in the ground. We've got the pushing force and the friction force the same. So these forces are in balance. When it's rolling down the hill, okay, no longer in balance. We've got the force of gravity going down. So we've got the opposing force going off the surface. And we've got friction going backwards. We notice that this one's a bit bigger. So the resulting force is going to be a lot that way. Unlike you're going to have a 30-degree slope at a shopping centre in a car park, but this is the diagram that I found. And the third one, when we have the collision, that force in that direction, not just the friction force, that's a force that the car applies on the trolley. And we notice that it's much bigger now because it's stopping it. Much bigger than all of the other forces. If a trolley has a mass of 120 kilos and hits a car with a force of 620 newtons, what is its acceleration when it hits the car? Force is mass times acceleration. 620 equals 120 times acceleration. So acceleration minus 5.2 meters per second squared. It's minus because it's slowing down. Got a few different aspects to this one. So we want to know how long it'll take to fall to the ground and what's the initial speed of the rocket. What is the initial speed of a rocket flying vertically at 1400 meters a second? If it's accelerating at 9 meters per second squared for 27 seconds. So we've got the final velocity, which is the 1400. We're trying to find the initial velocity. We've got the acceleration and we have the time. So here's the initial velocity we're trying to find out. So we find out that it's initially traveling at 1157 meters per second. Now we want to know falling to the ground, it's 2650 meters above the ground. Now its horizontal speed doesn't matter to do with gravity and how quickly it'll fall to the ground. Something that is flung outwards parallel to the ground will fall to the ground as quickly as something that is just dropped. It'll just be further away. Time to fall. Got the distance, which is 2650. What's the initial velocity towards the ground? It's 0. So that gets cancelled out. So let's have a look. 2650 for the distance, 0 times time, because the initial velocity is 0, it hasn't started falling yet, plus half times a, and a is gravity, times t squared. So we can work it all the way down till we eventually get the square root of 540, and we get 23.3 seconds. Does that surprise you? 2.65 kilometers will fall to the ground in 23 seconds. It's going pretty fast when it gets there too. And that is all.